Good evening and welcome to another exciting edition of Doing Physics with Mr. Bowers. So this evening we are going to look at forces and force diagrams and what those things are all about. So I'm going to begin with a couple of definitions. So to start out with, we have to define our basic terms here. What is a force? Okay, so its most basic level, a force is a vector. This is essential that we understand this. It has both size and direction. The one we looked at today in class would have been weight. Weight is down. It is a force directed down. Okay, and we are going to define a force as any interaction between two things. One thing cannot exert a force without the other thing exerting a force back. Forces always happen in pairs. It is an interaction. One person cannot interact with themselves and takes another. Okay, so forces always appear in pairs. When you're attempting to identify forces, make sure you understand that idea. Always in pairs. So when we are labeling a force, we're going to adopt this kind of notation. We're going to say F for force, capital F. We're going to identify the type, so we'll talk about that in a moment. We are then going to go with the, and the reading might say something else, but this is what I like. I like to say of the agent on the victim, for lack of a better word. Okay, so something causes the force, something receives the force. That's not how you spell victim. Anyway, we're going to identify this, but forces always occur in pairs, so this agent-victim idea, this flips back and forth depending on the situation. And we'll talk about that as we get into our cat up here. Okay, so that's your basic idea of what's going on with a force. I really need a bigger eraser than this. Yeah, this eraser. There we go. Oh, whoa. Yeah, whatever, we'll just get a new one. Alright, so there's our basic idea of what is a force. Now it comes down, we need to identify some things. Some other basic words. What is dynamics? This unit we are moving into here is called dynamics, and this can basically be thought as the analysis of motion through forces. Okay, in the previous unit we looked at how things move, how they move around, and how to describe how they move around. That's called mechanics. We're now going to look at dynamics, which is this, and it's really the why. Why do objects move the way they do? And how can we understand it to create predictions? Why do objects move the way they do? Okay, so that is the unit we are going into, dynamics. Great. Alright, so now let's actually get to work here. Uh-oh. New. Don't save. There we go. Okay, so we're going to look at this cat. We're going to draw a force diagram of this cat. A force diagram is simply a way to analyze the forces acting on an object. The first thing you're going to do when drawing a force diagram is draw a picture. Draw a picture of the thing of interest called the system. The system, that is the thing we're interested in. In this case, that's the cat. We're interested in the cat. And you're also going to draw the surroundings. That's everything else. Yeah, the surroundings. Great. You are then going to identify all interactions. Identify all of the interactions. You're then going to represent each interaction with a vector. And just like our velocity vectors from before, these vectors should be in the correct direction, and their magnitude, the length of the vector, should represent the magnitude of the actual thing you're talking about. Okay, so let's look at this cat. There's the cat. Let's make a list. We're going to identify the pictures there. There's the cat. There's the rug. Let's identify all of the interactions. So, first interaction, cat, or actually let's do it this way. Let's make a list of all of the things that are interacting with the cat. So, here's the list. The earth, which we identify as EE because it's not just a chunk of the earth, this is the entire mass of the earth pulling on the cat. We also have the rug. These are the two things which are touching the cat, so those are the two things we're going to interest ourselves in. Now we're going to actually draw our force diagram. There's our cat. We represent the cat by a dot. We're now going to go down our list and check these things off. The earth pulls down, so I draw an arrow directly down. I label it. This is F. It is a gravitational force. It is a gravitational force. It is by the entire earth, and it is on the cat. So there's one force. We also have the rug. If this were the only force, the cat would be falling. The cat is not falling. There has to be something else holding the cat up. So there's this vertical force. This is called a normal force. It is by the rug on the cat. We now have both of our forces, and we are done. We ran out of interactions, so we ran out of our forces. We want to identify using equality marks. We know that this force and this force must be equal because the cat is not in motion. If the gravity were bigger, the cat would be falling. If the normal force were bigger, the cat would be launched up in the air. Neither of those things are happening. The cat is what is called in equilibrium. So here's an important word. Equilibrium. This means the summation of the forces is equal to 0 newtons. You add up all the forces, you get 0. This force plus that force goes to 0. We know that because the cat is in equilibrium. Okay, so let's enumerate while we're here. Not going to talk about gravity. We've spoken about gravity, but let's talk about this normal force. All right, what is this thing? This is the interaction between an object and a surface which is perpendicular to the surface. Surfaces, generally speaking, an object can only exert one force at a time. However, surfaces are special. They can exert two. One of the forces that a surface will always exert is the normal force. Always. Every time there is a surface exerting a force, it is a normal force, and it is exerted perpendicular to the surface of interest. So there's that, and like I said, we're not going to go into gravity because we've already spoken about that in class. So let's go down and look at another example. See if I can center this guy. Here we are. Okay, so here's our skater. There's the thing. We have our skater. Isn't he lovely? Where's my mouse? There it is. We're going to go through the exact same process. We're going to make our list. What interactions do we have? Well, the earth is pulling down on the skater. The surface, which is the ice, is also exerting a force. Looking at our guy, that's all. Those are all of the things that are touching this guy. So we represent the guy by a dot. We have the force of gravity acting down. This is by the entire earth acting on the skater. Okay? The skater is not falling. He is not a projectile. So there must be another force holding him up. This is the normal force exerted by the surface or by the ice. I'm not going to get all bent out of shape about how you label this. It doesn't really matter. the normal force by the surface on the skater. And the reason we have this notation, this what type, by what, on what, is because sometimes you're going to want to make up forces. You're going to be convinced that there is a force somewhere when really there isn't. And the easiest way to identify those things is when you can't fill one of these in. You must have an agent, you must have something receiving the force, and if you can't do both of those, then you're making up a force. Okay? So you'll know it when it happens. Always make sure that you're actually talking about an interaction when you have when you're talking about a force. So there we are. Notice there's no difference here than with the cat. This force diagram and the cat force diagram are identical. Okay, here's the key. The guy is moving at constant speed. As we learned from projectiles, if there's a force, an unbalanced force, there's going to be an acceleration. Okay, so here's the idea. Unbalanced force leads to acceleration. This actually goes either way. If you have an unbalanced force, there will be acceleration. If you have acceleration, that must mean there's an unbalanced force. Here's this skater. He's not accelerating. He's moving at constant speed. So that tells us there cannot be an unbalanced force here. The summation has to be equal. I'm going to add another layer here. You should always do this as well. There's a thing called the net force. That is the sum. That little symbol right there means sum. The sum of all of the forces. Well, these are vectors, so we add them like vectors. We add them component-wise. So we're going to break this into horizontal. There aren't any horizontal forces. And vertical. We have two. We have the force of gravity acting down, call that negative, and the normal force acting up. We know further that those two things have to also equal 0. There are two forces, but we know that they have to add to 0 because there's no acceleration in this case. So, there's another example. Oh, that is not the button I wanted. That, and let's pull up the next example. Let's actually jump ahead to something that's a little bit more interesting. Let's go here so we can talk about a different type of force. Okay, so we have this chandelier. Let's make our list of interactions. Now, the interesting thing here is that the system is the chandelier. That does not include the chain. So I'm actually going to redraw this. I can't draw on that picture with this setup, but here's the chain. Here's my chandelier. Okay, my system is going to be the chandelier. Okay, the reason for this is this interaction up here is ugly. We don't want to mess with that interaction, and it doesn't matter. So we can just ignore that interaction. This one is much easier. Okay, so let's make a list of all of interactions. We have the Earth, always the Earth, and we have this chain. We like the chain because this introduces a new word. This is called a tension. Tension is force in a rope. That's it. And here's the deal. You can't push a rope. The end. You cannot push a rope. You can only pull a rope. Tension is always along the rope, and it is always that's it. It's always along the rope, and it always pulls. Ropes pull in both directions. That's all. So let's draw our force diagram. Here's the chandelier. Gravity pulls down. F gravity by the Earth on the, can't spell chandelier, can't be the only force, because if this were the only one, it would be unbalanced, and the chandelier would be falling. That isn't what's happening. There is a balancing force. This is a tension, capital T. Tension, there it is, force tension. I just use capital T's by the chain on the light. Another important feature, this ending bit should always be the same as the thing in the middle. Notice how we're drawing these vectors on the object of interest, the system. If you end this in anything other than your system, you have a problem. These forces must be on the object of interest. So make sure you check that as you are working. Don't get this backwards and don't start putting forces on here that are actually acting on something else. This isn't a whole lot different than the last two. Again, getting ourselves set up. F net in the X direction. There aren't any. F net in the Y direction. There's the tension minus the gravity. Those have to go to 0. We know that because this light is not accelerating. Objects which are in equilibrium, that is not accelerating, have 0 net force. You add up all the horizontal forces, you get 0. You add up all the vertical forces, you get 0. So there's that. Let's look at this bucket. Okay. Here is the idea. The bucket is the system. It's the bucket. So we want to make a list of things that are interacting with the bucket. Here is that list. The end. Lots of people want to say, oh, but this guy, he's like pulling this way, right? Well, yeah, but the guy isn't pulling on the bucket. The guy's pulling on the rope. So the man exerts a force on the rope. The rope exerts a force on the bucket. They're different things. If the system is the bucket, we only care about forces on the bucket. So here's the bucket. Force, gravity, by the earth, on the bucket. That can't be the only force, otherwise the bucket would be falling. The bucket is being lifted at a constant speed. That means acceleration is 0. This implies that we are in equilibrium, which means the net force is equal to 0. So we need another force. Luckily we have another force. This rope is pulling straight up. You can see it in this picture. There it is. Okay. In this picture, the rope is pulling straight up. Ropes can only pull. They can't push. They can't go off at crazy angles. The rope is going up, so the force is going up. This is the tension by the rope on the bucket. Checking again. Bucket, bucket. We have only forces which are on the object, which is the bucket. Notice also, all of the forces point away from the object. We begin them on the dot, and we go away from the dot. Even if it seems like it should be the other way, it doesn't matter. We always begin the vectors on the dot and move them away from the dot. Okay, so there's that one. Like I said, the common mistake is people want to say, oh, well, this rope is pulling off this way. That has nothing to do with the bucket. Again, the man pulls on the rope. Great. Okay. While we're here, this picture also gives us the opportunity to talk about pulleys. So this is a related thing. A pulley. This is basically a wheel. And when it comes to forces, all a pulley does is redirect a force. That's all they do. They don't change it in any way other than redirecting it. So sure, this guy is pulling this way. There's a tension. Oop, I can't write up there. There's a tension going along the rope because of the guy. What the pulley does is redirects that force straight down so that it affects the bucket. Okay? And again, tensions act in both directions. The rope pulls up on the bucket, the rope pulls down, or really over on the man. Okay? Ropes always pull, and pull in both directions. So there's some forces. Let us go to one that is a little more interesting. Like this one, number 9, if I could get that. Whoa! Uh-oh. Lost it. There it is. Let's look at number 9. Draw a force diagram for a ball that is at the top of its parabolic trajectory. I'm just going to click everywhere. So let's make a list of all of the things that are interacting with this ball up here at the top of its motion. That's right, there's only one thing. This is a projectile. Projectiles have only one force, and that force is caused by the Earth. So we get one force, the force of gravity by the entire Earth on the ball. I guess we're not in equilibrium. The net force in the x direction is equal to 0. The net force in the y direction is equal to the force of gravity. Interesting thing, we learned already that the acceleration in the x direction for a projectile is 0. Well, isn't that curious? And we learned the acceleration in the y direction is not 0. It is approximately 10 down. The force of gravity is down. So I guess I'm going to throw in my negative. It's down. The acceleration is approximately 10 meters per second squared down. There's a connection here. And notice this other thing. Acceleration is a vector. We do it by components. Force is a vector. We do it by components. The only thing that affects the horizontal acceleration is the horizontal forces. The only thing that affects the vertical acceleration is the vertical forces. Alright, so I'm going to wrap this up here. That is your crash course in sort of simple force diagrams. I'm going to do another one with a little bit more complicated force diagrams and talk about how we deal with those.